Good morning and welcome to Race Industry Now, the weekly webinar series from ePartrade, presented to you by ARP, Performance Plus Global Logistics, PIC, Ferrea Racing Component, and Fifth Third Bank Motorsports. I am Francisque Savignan, the founder and CEO of ePartrade, the racing industry, every minute, every day. This is episode 445, and we're going to be talking cylinder heads machining with MEC CNC and the AERA. With me this morning is Brad Gillie, as Judy is traveling to a NASCAR race in Texas. Good morning, Brad. How are you doing?
I'm doing wonderful. It'd be nice to see Judy here in the Lone Star State this weekend.
Absolutely. Excellent. But I'm delighted to bring Anthony Usher with us today. Anthony and I go back 20 or 25 years from his days at Rutler and my day at PRI. But we're also bringing back Chuck. Chuck has been on our series a bunch of times. So good morning, gentlemen. Without any more interruption, I think we're going to leave you in the hands of Brad, and you guys on.
Thank you, Francis. We'll see you back here in just a short while. Want to thank everyone for tuning in here today. And as always, want to let you know that if you have a question at any point during our conversation here, feel free to type it into the chat. We'd love to make sure that we're answering any questions that you want to know. But we've got a great topic and a great education coming up here today. Modern Machining Methods for Cylinder Heads by MEC CNC. And as Francis mentioned, our panelists today, Anthony Usher, the president of MEC CNC, and Chuck Lynch, the vice president of technical service for AERA. That's the Automotive Engine Rebuilders Association. And gentlemen, we're glad you're here. Anthony, let me start with you. First, tell us a little bit about yourself and about MEC CNC.
Well, thanks, Brad. Thanks, Francisque. Great to be on this webinar. I was chatting to my wife last night. It's just about 50 years since I first lapped a valve in. So I've been playing with engines and valves and seats and cylinder heads for a long time. I got involved in the cylinder head machinery about 40 years ago. I initially sold machines, and then I got involved in helping design and manufacture machines. And today we have a range of machines that solves a lot of problems with modern engines and performance applications and things like that. So I'm very excited to bring all my experience and knowledge to this webinar and see what we can give you guys and what questions you have for us. We look forward to answering them.
All right, we look forward to it as well. Chuck, let's talk about you for just a moment. Let's talk about your background and the AERA.
All right. So I've been in the industry about 34 years professionally, and add a few years for the non-professional side of it, more as a hobbyist and so forth. But I did this from my time in the military. I worked at a production engine rebuild facility for 20 years. I've been a service technician in the industry, worked as a production engine rebuilder application engineer for Moloch Levite. And currently, I lead the technical side of the team at AERA, the Automotive Engine Rebuilder Association. So all of our members of our team have come from shops, manufacturing, and things of that nature that helps us answer questions. We are an international trade association. So, I come in every morning to requests from, whether it be South Africa, Asia, whatever. It's very, very interesting, and it's great to be a part of it all.
Well, we're happy to have both of you here. By the way, I want to say hello. Russell Baccarella says in the chat, I'm broadcasting this workshop to my engines class at Cypress College. So welcome, Russell, and to all the students as well. I'm sure we're going to have a great education here. All right, well, let's talk about Anthony. I know we have a PowerPoint presentation that's going to help guide us along here throughout this webinar today. So some great visuals to go along with the conversation, some of the problems, some of the solutions, and things that we're talking about. So I'm going to let you share the screen and take it away, and we'll just sort of interject as needed. So go ahead, Anthony.
Okay. Well, basically, this is a presentation about precision equals performance, valve seat machining, valve and guide finishing, and head gasket surfacing. And I'm going to lead on the first part of this The first part of the session is where it all begins, the valve guide, and it's the heart of any valve train situation in a cylinder head. And I'm going to let Chuck say a few things about the valve guide and take it on from there.
All right. So, as Anthony just mentioned, the valve guide is utmost importance. And, when we get in, the cylinder heads in, I think one of the things that we just don't give enough credit to is the importance of that. There has to be a point of origin, right? Everything has a datum. So you can't produce accurate valve seats if you don't first have good guide bores. If the reference point for the seat is subpar, the seat quality will suffer. So, I like to summarize that in the valve guide is the guide, not the seat. Now, one of the things that we often see is people will vacuum test and they vacuum test well. And you're in essence kind of putting two funnels together, and they will vacuum test pretty well because you can flex parts. So you just really have to pay very close attention to the valve guide. So machining the guide bore should be finished without any tearing or out of round or taper. The desired method to finish the guide is honing, to make sure you're straight, true, round. A lot of people ream to get close, but ideally you want to, then finish the bore so you can really control surface finishes. There are hand tools and machines out there that can finish hones to accurate diameter and surface finish. Anthony, you want to jump in on that? That's your world.
Yeah. Thanks, Chuck. Yeah, we focused on guide bore finishing, and we know the guide is the most important thing before we even start on the valve seat. So at Robbins, we've been developing machines to do all the guide work with heads of integral guides. We've got core drill system where we can core drill out the heads so you can install loose valve guides. We then have reamers that can bring the guides to close to size, and then diamond hones to finish them. And we've got a machine that does all these processes, and we're able to finish guides to very accurate tolerances, straight, round, and on size as well. And that's the most important part of starting the whole before we get onto the valve seat. So we'll move on to the valve seat, and a few other things about the guide that can create some problems with the seat. Of course, random seat run out often comes from guide problems, chatter when cutting the seat, and problems like that. Of course, vacuum as well can come through the valve guide. So let's go on to a little bit about the valve seat. Now we've got a perfect guide. Let's talk about the valve seat and what we need to get there. Chuck, would you like to come in a bit on the valve seat?
Sure. So the primary function of the valve seat is to provide a combustion seal. We all know that. It's one of the reasons we kind of vacuum test. So concentricity or seat run out should be less than the stem to guide clearance. We get the question often on the tech line. People look for this, in my past, in the shop, everybody's looking for some kind of rule of thumb number. Hey, what can my valve seat run out be? And you really need to think about, well, where am I trying to put my stem to guide clearance? You cannot have more run out than you have stem to guide clearance. I'm going to go back to my little analogy of the funnels. I have two tapered angles that are going to wedge together. So anybody that's familiar with machines, they're familiar with the terms Morse taper, R8 taper. You have taper force is exceptionally high. So I can get those two wedges to come together, but what's going to happen to the valve stem? It's either going to flex the stem, but that stem's going to try to move proportionally. So in seat and guide machines, we often have an issue with perpendicularity, more so than off center line. So as the form tool moves up and down, it it tends to tilt the seat. So with that high wedge pressure, now the valve stem is going to move and it's going to be rubbing against the guide. So again, I tend to go back to what are you trying to establish for stem to guide clearance, and your seat run out cannot exceed that. And you also desire a surface finish of a valve seat that's without chatter or undulation. Chatter, we all know what that is, but undulation is like a deviation in off the center point. It still shows up as like a high point on the seat, but as you have deflection and react, it's kind of a vibration kind of tendency. And again, you'll see that with chatter. They're just at a lot different frequencies. Anthony?
Well, Robin's valve seat guide machines are well developed, a few thousand machines in service worldwide, up to nearly 30 years, and some doing 30, 40 cylinder heads a day. And these machines can get these finishes on the guides that Chuck's talking about without chatter, without undulations, and with very little run out. And the better the valve guides are finished, the less run out we get. And these machines have multi-angle seat cutting inserts, which can have different profiles, different angles, different widths. So all that process is done in one cut. And of course, the centralizing pilots that are used for seat cutting are manufactured from solid carbide, ground to very high precision. Being carbide, they don't flex, and they have very little wear on them. Robins have been developing some new technology valve seat cutting systems. We found cutting with a single insert creates some side thrust, and we've now developed some tools that have dual inserts, so 180 degrees opposed, and we're finding that this cutting system is reducing side loading on the cutting system, giving better finish, much finer finish, and reducing run out once again. I have a photograph of a setting instrument we provide now. On the top left corner there, it's a very precise instrument that has a dial indicator, and we actually set the diameter of the seat from the outside of the insert. So on that insert drawing, highlighted in green is F1 dimension, and then I highlighted in blue that dimension from the edge of the insert to the top diameter of the valve seat. We add that dimension into the setting on the instrument, and we can set the exact diameter of the valve seat in the cylinder head. So we don't have to have pointers on a valve. We can dial in exactly the diameter we want. Both insert holders are on adjustable slides, and the dial indicator will tell us that we have that exact diameter. We also provide this tooling system for counterboring housings for new insert rings, sometimes used for boring out old insert rings. Some insert rings are very hard to get out mechanically, and you've literally got to cut them out. So having dual insert tooling, it speeds up the process, and again, we get very accurate boring sizes for these inserts. Another important thing with valve seats is heat, and heat in the valve head. 75% of the heat of a valve head is transferred to the valve seat. This photograph here actually shows a water-cooled valve seat on quite a high, it's a natural gas engine, runs very high temperatures, and they actually circulate water around the valve seat insert to cool the valves. And also, of course, to cool the valve seat. And Chuck, I remember the other day we were chatting and you had something to say, the valve seat is not the guide. Maybe you want to say a few things about that?
Right. Yeah, I said that earlier in the presentation, and you just really need to drive that point home that, again, as that taper, I have that high wedge pressure. Some of the racing heads have, 55-degree seating angle. So with that high wedge pressure, you can create a lot of flexing. And moving on, as you mentioned about transferring the heat from the valve into the casting, the importance of not only run out, but contact, that you are making good full contact. And, in the racing world, this is not even, the RPMs that we see high, but, just for simple numbers, you say 6,000 RPMs, the valve's opening and closing 50 times a second, and your exhaust valve may go from 500 degrees F to 1,300 degrees to 500 degrees F. And we're doing that, 50 times a second. So sometimes it's just hard to fathom what the valve seat has to stand up to. So if we talk about continue on the valve to seat contact, in the past, I worked on this a lot, trying to get to the point of having full face contact and non-interference angles. And quite honestly, even in shops where you can spend a tremendous amount of time on the valve seat job, it's just impractical because the seat seat insert manufacturer has a tolerance, right? So Anthony, I would think that's usually plus or minus 15 minutes.
Yep.
On the insert. Well, the valve supplier also has that same tolerance. So the probability that you're going to be able to have full face contact is quite unreasonable. And then you also have cylinder pressure that is pressing against the valve head and is going to force that to the seat too. How much really depends on how the valve is designed, how heavy the head is, margin area, the materials that are used, and so forth. So at a minimum, you can kind of look at that illustration. You want to make sure that your contact is out closer to the margin and not hitting nearer the neck of the valve. So if you have that situation, you're going to have a valve that's going to overheat, tend to burn the valve. Anybody that's ever taken a torch and put it to a piece of sheet metal or something, where does the heat go fast? It goes to the corners. It goes to the thin areas. So if you have the contact that's hitting closer to the neck instead of, closer to the margin, then that thin area is going to overheat. So again, it's pretty impractical that you're going to get full face contact, which would be, ideal, but definitely you want it up on the upper margin area of the valve.
That's
Anthony?
really interesting. Yeah. I'm just curious. And we do have a question from the chat that I want to throw out there now. It might apply a little bit later on. And if someone wants to ask one, by all means, feel free to type it into the chat. We'd love to answer anything that we can. I'm curious when we start talking about now braking parts and obviously the precision in this and not only the surfaces themselves, but you talk about where the seat is. Where do the biggest problems come from when we're now talking about braking parts and having some inaccuracies in this?
Well, nice question, Brad. And look, the screen I just put up is all about focusing on braking valves. I mean, we've all heard about a dropped valve, and the head of the valve comes off and it flies around the chamber and it destroys everything. And we look at it and we see, we had a bad valve. The valve broke. And we get a hold of the valve manufacturer and we say, you don't have a good valve. Your valve destroys my engine. Meantime, 90% of the time, I estimate 80, 90% of the time, a broken valve is from a valve seat run out. And this drawing on the left shows where a valve is contacting on a high spot in the valve seat because a valve seat run out. And you can see that it flexes and bends the head of the valve. And it also puts side loading on the guide, so excessive guide wear at the same time. But as far as valve breakage goes, I'm going to say 80, 90% of valves that break are from seat run out, not from bad valve quality. What do you think, Chuck?
I agree. There's a ton of movement in castings, thermal movement and so forth. But it's one of those situations. If you aim small, you miss small. This stuff is very, very high frequency. We were talking about, at 6,000 RPMs, the valves open and closing 50 times a second. And I'm sure we've all broken a wire hanger by flexing it. Now, this is happening at a much higher rate than that, but that's what's going on. We have flexing that's fatiguing the material, and it breaks. When you get lucky, it wipes out the guide. I think, oftentimes when we look at worn guides, we're not thinking about the high seat run out, which loaded the valve against the guide, causing the issue. We're like, oh, we blame it on heat. We blame it on, bad guides. We blame it on everything else. And sometimes, it's because we don't know what failure looks like. Kind of use the analogy, you don't know what you don't know. But when you do learn what the point of origin is, and somebody helps with that stuff, then you start to look at it through a different lens, and then dumb luck goes away. It's like, okay, I have seen that failure before, and I've seen that failure for 20 years. I just didn't know what it looks like.
Yeah.
So I think that's really important to keep in mind here.
Yeah, and there's always some instruments for measuring valve seat run out. Here's a photograph, a very common instrument that can quickly measure general valve seat run out. And of course, vacuum is very important. So when machining valve seats on a machine, it's important to do vacuum testing before taking the head off the machine in case you don't have a full vacuum. And it's also very important to do leak down testing. A lot of vacuum testers will draw vacuum, and if there's a small leak, you won't see it. But when you turn the vacuum tester off, it'll show leakage, and that can detect some problem with valve seat contact. And two kinds of vacuum testers. One is driven by compressed air, the photograph on the right there, and the one on the left is electric driven. And literally there's a valve that'll turn off the vacuum pump so you can measure leak down.
Right. So yeah, vacuum decay, there are some standards around that. And, I would just like to add, both of these tools individually are good tools. So a lot of folks vacuum test, but they don't have concentricity gauges. It's something that needs to change in the industry, because it helps you tell the condition of your equipment. If I have consistent run out that, say, at 2 o'clock on every valve seat that I measure, I have something set up in, probably with my machine I can adjust. If it's random, it's guide sizing, pilot selection, something of that nature. If it's a machine with a steering wheel, I call it torque elbow. It's the operator. So if you have random seat run out, that's a tougher thing to address, but it can very much tell you what's going on with your machine. Now, if you think about this, some of the things, like you can have high frequency chatter and it'll still be within specification as far as run out. So it's less than a thou, but you will not pass leakage. On the inverse, I can have a nice uniform run out, say 7 thousandths, but again, if that vacuum pump's got the capacity, it'll flex the valve head and it won't show a leak. So, both of these, it's the whole Stephen Covey kind of thing. 1 and 1 can equal more than 2, right?
Yeah.
So, and if you think about this, if you're doing a leak down test in an engine, now a leak down test, if I have a bent connecting rod or something, I'll leak to the crankcase. But I could actually have an engine that doesn't leak down, but it has the wrong connecting rod in it. So cranking compression would tell me that something's wrong, and the leak down test would say it's good. You have kind of the same thing, concentricity with vacuum testing. So, again, there's some synergy in having both of these test equipment pieces.
Well, some little things on valve seat machining challenges that can create problems when cutting the valve seat. And one of the points that I often find is people extending tool holders out to their max or even past their max radius dimension creates flexing and can create vibration. So most rigid tool holding is is the most desirable process to cut the valve seats. I think we should also talk a little bit about the valve itself. When we talk about runout, we often talk about seat runout, and sometimes the valves themselves have runout. New valves, reground valves often have runout, and they create similar problems to what we mentioned before with seat runout. So this is an instrument that can be used to measure valve runout, and in some cases we actually have stem runout. So this instrument here is quite a sophisticated instrument. It can quickly be moved with the indicator on the valve stem to see any stem runout, and there's other devices available in the market just for measuring valve seat runout, or the seat part of the valve runout. And I always recommend even new valves. We find new valves can have up to 1 thou runout, and that can create vacuum problems. Well, you can find them with vacuum, and sometimes you think it's the valve seat. Meantime, it's the valve that's actually got runout.
Yeah, and actually an interesting thing that you can also do, you measure, you mentioned the stem runout, but you can also pick up on the shape of the stem. So say when the manufacturer is making the valve, if you have, it's just like cylinder honing, the different orders of geometry. So if I have slippage in the centerless grinder, I can have lobing on the stem. And sometimes it shows up after the engine's run in the guide for a while, and you'll see it looks like it's got tiger stripes or something. And that's a condition that makes it difficult to grind the valve face, because it's not going to repeat, especially if I'm running a centerless valve face grinder. Now I have situation like that undulation we were talking about in the seat earlier. I can have situations with the grinding of the valve face. I could have oil consumption because of the valve stem seal not actually contacting the stem properly. I know that 75% of my temperature goes out through the valve face, but there's still a percentage that goes out through the valve guide. So if I reduced my contact area with the guide, now I may potentially overheat the valve stem and then have a failure. So there's a lot of good things that can come from a tool in measuring a lot of different areas of the valve.
Thank you.
Yeah, well said. And I know we sort of just talked about this breakage just a moment ago, and I think this is a great illustration of it, Anthony.
Yeah, I think so. It really shows if it's valve run out or seat run out, that's flexing on the head and wear on the guide. Okay, that's a typical machine, a Robbins valve grinding machine. This machine will grind a valve within 1 to 2 tenths run out, and can also accurately dress the butt end of the valve and chamfer the butt end of the valve. Well, let's go on to talking about cylinder head gasket surfaces, and three important things. And I'm going to hand this back to Chuck. He's the expert on this head gasket surface.
So, surface roughness, flatness, waviness has always been important. But if you take a look at the modern engines, what percentage of them are using MLS gaskets? MLS is the acronym for multi-layer shim gasket. And they have taken that to definitely next level. This stuff has to be flat. It has to be smooth enough. And, when we talk about flat, you have overall flatness, but you also have the waviness that's created typically not by, your insert or something of that nature. It's going to be induced by how rigid your setup is, or, machine features. There are a lot of old gear drive machines that maybe induce waviness in. So those are things that we have to look at today that we didn't once give a whole lot of consideration to. So this illustration here is a good example of, I look at lay or direction. So if we have a milling insert that's traveling in a particular path and you get that, semicircular pattern that's left on a gasket surface, that's your lay. The waviness spacing, again, that's what's induced by your frequencies within the machine. the waviness height, and then the roughness height. So roughness height and waviness height are totally different. And so you can have a roughness that's ideal, but have excessive waviness and still have similar type failures. So there's a lot going on with surface finish.
Yeah, I often say to people, roughness it's an instrument that measures about 100th hour travel. This is a diagram of an instrument measuring it and the stylus. So a simple entry level roughness measuring instrument normally travels about 100th hour, and that'll measure roughness. But to measure waviness, you need to travel approximately 1 inch. And I think we have some information here on it. But a roughness instrument is a little bit more sophisticated, a little bit more expensive. But that's what the MLS gasket people are talking about today: waviness. What does it look like over a long distance, not just a short distance? As Chuck said, roughness can be good, but waviness could be poor.
Right. Something simple for the folks that maybe aren't into the engine machining part of it on a day-to-day basis. People are always interested by measure, and when we talk about measuring surface finish is the most accurate stuff that we're doing in engine building. And it's extremely important. We've done a lot of stuff on cylinder honing as of late, been a ton of good presentation on that. Mark Malberg's been helping out on a lot of these different areas of surface roughness, flatness, waviness, and so forth. But when we're talking the roughness for these gaskets and piston rings and so, if you were to take a hair follicle, which measures about 3 thousandths, and you were to take that follicle and look at the column end of it, you're going to slice that 2,000 times. And that's the kind of stuff that we're measuring. So just to, put a real world kind of measure to that, that's how small of a scratch in the surface matters. So anyway, surface roughness can impact the gasket's ability to perform in the short term and the long haul. Aggressive surfaces can shear gasket materials. Back in the day, we used to say, oh, we need a gasket surface that can bite the gasket. Even with composite gaskets now, those days are kind of gone because we do heated pre-flattening and there's the coatings and so forth. We don't need that anymore. So aggressive surfaces wear down quickly. They allow combustion armors to move and ultimately leak. This is also often observed as fretting or false Brinelling when evaluating head gasket failures. Aggressive surfaces can cause cold sealability issues, whether it's an MLS gasket or a composite gasket. Now they apply some silicone type materials to help with that cold sealability. The aftermarket even more so than the OEs because you don't know who's going to get your gasket and use it. Surfaces that are too smooth can allow gaskets to move around or flow, which can lead to failure. That's not so much the issue with MLS gaskets because we typically won't take time to make it too smooth. If we're using milling or grinding, we're just not going to get there. You would have to lap the surfaces. So it's not so much of an issue anymore. If you want to go ahead. Surface flatness is, this is in service manuals and so forth now, and people use a straight edge and a feeler gauge, and it's just about gotten to the point where it doesn't bring a whole lot of value. There's too many surfaces to check, in small little areas. Well, if I got a feeler gauge that's a half inch wide, and I'm measuring an area that's a thou out of flat, you have to measure so many areas to indicate that. So again, I don't think this is much value anymore. Most everything needs to be resurfaced. If it was taken off and went to a shop, you better resurface it. That's, that's strictly an opinion, but that's kind of what the industry yields anymore. Let's see here, roughness versus waviness again. So We talked about that pretty good. The bottom picture, that roughness profile, that's that kind of sawtooth pattern created by the tooling. The waviness profile is, again, it's set up by the environment more so. And I say the environment being the machine, the fixturing that you put your cylinder head or block or whatever on.
Yeah, and that's a great illustration too of again, just what impact the waviness is going to have, with the higher points and the lower points versus just you sort of have the same peaks on the roughness side, whereas the wavy side definitely going up and down. I think that illustrates very well what you were talking about.
Yeah.
Right. An MLS gasket doesn't conform to those waves like the conventional gasket does. So it's kind of like a suspension bridge. It's under tension, so it's not sagging all the way to the very bottom of that valley. So it just doesn't conform. So I have a leak path under there and over a long distance. Now, I've dissected a lot of MLS gaskets over the years, and they hide things because of the coatings and the type of material it is. You don't see some of the indications that you would see in a conventional gasket. But one of the things you can do is drill out the rivets and lay out the layers. And sometimes you see where combustion went between the layers of the gasket. And again, it looks like tiger stripes or zebra stripes or something. And that's an indication of waviness. So stuff was moving between the layers of the gasket that didn't really show up on the face so much. So that's kind of a good thing. You say, hey, if I've got combustion in the cooling system, hydrocarbons, or whatever, then maybe I take that gasket apart. So, all right, some factors that influence roughness and waviness. The cutting to insert, PCD works terrific for aluminum, but will fail quickly when cast iron. CBN works for both, but usually you tend to see some smearing on the aluminum. The aluminum galls to the insert a little bit, and it may not even take it out of the roughness and waviness parameters, but visual, which, we do a lot of visual identification of what we feel is good or whatnot. So sometimes, we use the PCD, the polycrystalline diamond, and we just really like the look of that. The insert edge prep and condition, tooling suited for iron, but not aluminum. You could have a situation where they call, the edge prep of the insert would be honed or have a taper they call a land. And if you take away that sharp edge, it's less likely to chip. So it gives you more durability over a longer period of time, but you also tend to have more tool lift. So you may not get as truly flat of a surface or as you would with a very sharp insert. So again, you got what does the tool yield? What can I tolerate? Machine setup to, include level, secure feet, head clamping, etc. So, the machine needs to be parallel is kind of what we're talking about when we're level. When you're cutting the surface, you just need to make sure that, the fly cutter or the milling head is producing parallel surfaces. Secure feet is one of the things that I've seen oftentimes is people have forklift traffic around the machine or something, or they bumped into it. And then now I have an unsecure machine and they have surface finish issues and we complain about the machine. Well, it's not even really the machine. It's just, that outside influence. Holding the part is another extremely important thing. Having a maintenance program, and we have a podcast ourselves, and we actually did one on equipment maintenance. And most people, they say, I perform maintenance after something broke down. No, you're dealing with chaos at that point. Maintenance is preventative, and to check out your equipment and, set some schedules and say, okay, this many hours I'm going to do this many hours I'm going to do, and you won't end up with some of these situations with roughness, waviness, or whatever. Because, we have crashes that bring on some of that stuff immediately, but usually it takes time to get to that point and we start to ignore it. So that's a good thing to kind of keep in mind. Spindle condition, bearings, again, it goes back to the preventative maintenance. And then speed and feed's the one that people typically think of the most that impact their roughness. Where waviness could kind of come in there is, hey, do I run my machine faster than the capability of the machine? And then I could induce some waviness and so forth, because then I start to get out of balance or something.
Mm-hmm.
Again, I think we kind of covered this pretty good, measuring roughness versus waviness. The device to measure waviness is a skidless instrument. Skidded instruments are used to measure roughness. So the skidded instrument will set right on the part, and the skidless instrument, which is shown there, you isolate it from the part that you're actually measuring. So again, that goes into more detail about the device of the that's being used. But again, if you're going to measure waviness, you have to kind of step up to the next level of equipment, which is a skidless profilometer.
I'll go on to this solution and the Robbins machines. We at Robbins have done a tremendous amount of development on surfacing with these three factors: roughness, waviness, and flatness. And the whole design of the machine, the precision ball screws, the servo motors, belt-driven servo motors driving the ball screw, all these factors have come together to produce extremely accurate roughness and waviness. And of course, the whole accuracy of the machine will also induce very accurate flatness. So these three factors are what we have taken into account with Robbins surfacing machines. We can handle from very big heads. This head is nearly 44 inches long, and we can handle down to very small heads, single cylinder heads, and produce those three factors to very accurate tolerances. Well, that's about all I have from my side for now. So
I'll say
some questions there, Brad.
Yeah, for sure. And by the way, for both of you, that was what an education. From both you and Chuck, from you, Anthony, and Chuck, and obviously what a great solution as well, Anthony, with Robbins. We do have a couple of questions. This one says, what sources are there for cylinder head / block dimensions, architecture, datums, locations, angles, etc.? So, I guess this is maybe, what sources are there to make sure that we're having the right accurate measurements, angles, and all of that?
So we do have some of that information. Of course, it's a challenge. There's the Right to Repair Act that that stuff's being fought constantly about our ability to repair. So trying to get that data can be even more challenging than something like what's the cylinder bore size and, what are torque specs and crank dimensions and so forth. But SEMA does have some of that information. If you're SEMA members, we have some of that information for members of the Engine Rebuilder Association, are a couple of outlets. Sometimes you can get data points from part manufacturers. If they're making a part, they may share that. They want their stuff to be successfully installed too. So a head gasket supplier may tell you where the bore location should be relative to the head gasket dowel, because their head gasket is not going to live well if you say centering fingers to bore a cylinder. So someone else has worked on it and they moved it. Now you're working on it again and you move it further. Now the head gasket hangs into the combustion opening. The gasket doesn't have much of an opportunity of, survival. So just kind of think like that. Another thing I'd probably throw out there though is, just because parts are available sometimes doesn't mean that all of that research has been done. So, what is that old saying? trust but verify, So
Very well said. Sound advice. All
Right.
right. Any importance to be placed on teardown analysis, microscopic examination of wear/damage to head off potential failure premature? When you're taking something apart, you've talked about different things from tiger striping to a lot of, other things. What do we learn as far as when we start pulling things apart after they've been in use?
I think that's a terrific question. I had mentioned earlier that like the false Bernelling of the gaskets, the engines now make even the stock stuff. Randy Neal said something at one of our production engine rebuilder conferences a few years ago, and he said, "Who builds high performance engines here?" No one raised a hand because it's production engine rebuilding. And he said, everybody in this room. I mean, you take the example of a 3.5 EcoBoost, twin turbocharged, the power per cubic inch is crazy anymore. Everything out there. So all of the materials are being tested. So if you start to look at the gasket surfaces and you see that there's, the embossment on the gasket is worn into the aluminum head. So a lot of that high frequency type stuff. Okay, is there a better gasket out there that has more layers in it that accommodates that movement more? You look at from the OE standpoint, they're going to go with as few layers as they possibly can to make that gasket. Hey, I want it to live 110,000 miles or 150,000 miles or whatever, and then we don't have to worry about it anymore. But in the racing world and so forth, we got to consider something different, or even, automotive repair. We have to think about, hey, how do I combat that problem? The OE was, say, 3 layers, but it really needed 5 or 7 layers because there's just too much movement. So you can definitely take a look at what is yielded by the teardown. And actually, partner, in our podcast, Steve Fox and I were talking about that. It is so valuable to have a teardown person that just questions everything. It's your engine is sometimes the dead body. You may not have the complete crime scene, but you can use that as an opportunity to say, okay, how do I make sure that high cholesterol doesn't get this guy? And we actually use that term, with turbocharger failures that get coolant in the oil, the turbo cholesterol. But anyway, there is a great amount of opportunity to be gleaned from, these previous failures and what you can do to adjust for it. So improving surface finishes. And so anybody that works on LSs, they know that the main caps are absolutely horrible. The contact area is really, really terrible. So they redress the main caps. Some of the OE surface finishes are very aggressive because they're trying to produce 2,000 engines per day or whatever. So yeah, we can use that as an opportunity and offer something better.
Well, Anthony, when it comes to solutions, obviously with Robbins, we're talking about what some of the problems are and what you guys have to resolve those. Tell us about Robbins. You guys are USA based, direct to the shop. You've got some great products here, obviously.
Yeah, Robbins has been manufacturing cylinder head machinery now for 30 years. And we have a wide selection of machines for startup shops, guys doing just small engines like power sports, motocross bikes, and then we have mid-range machines for. I just set up a whole shop with new machines. They do pickup trucks, so for 6-cylinder inline is all they do. Biggest they'll do, and then we have large machines where you can put up 24-valve diesel heads, single cast heads, and machine the whole head in one setup. Roll the head over, do injector tubes, all that kind of stuff. And likewise with surfaces, we have 3 different class of surfaces: entry-level machine with a universal fixture, and then we have advanced machines for production rebuilders, such as Chuck mentioned. So the other really, the latest sort of technology we're working hard on at present is the guide machine, finishing guides, honing guides. Most people in the high-performance industry are honing guides by hand. It's a very stressful job, takes a very skilled guy a long time to get the results. the Robbins guide honing machine can achieve very accurate results very quickly and very consistently. So that's an exciting product that's going into some high-level shops at this stage. We often say people spend $150,000 buying a block honing machine, and then they run a hand reamer through a guide. They don't even look inside the guide. And when they do look inside the guide, it looks too terrible. So we're really getting people to focus on the guide, focus on the finish, measure the guides, and improve the quality of the guides, because that's the best way to improve the valve seat and prevent failures and improve performance.
Well, gentlemen, this was an incredible education, and again, incredible solutions for some of the problems that people can run into with Robbins and what you have at MECC&C. So, Anthony, Chuck, we can't thank you enough for giving us time today, and certainly a great education on talking about surfaces and valves and all of that. Francis?
Absolutely. What a great webinar. Thank you so much, Anthony. Thank you so much, Chuck. This webinar has been recorded. It will be posted later on the ePortrait platform, distributed through our newsletter and social media channels. In the meantime, we pushed MECC&C and Robbins machine back on the homepage of the ePortrait platform. So please go to www.eportrait.com and you'll find out absolutely everything. Next week webinar will stay with engines. We're going to be hosting Shaver's racing engines. And again, thank you very much for being with us today. Please, for more information and updates, www.eportrait.com. Thank you and goodbye.
Thank you
very
Bye-bye.
much.